Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into a fascinating guide on scaling large language models, specifically focusing on the challenges and strategies involved in maximizing performance on massive hardware setups. It's all about getting the most bang for your buck, or rather, the most flops per dollar.
Exactly. I'm particularly excited about this because, scaling isn't just about throwing more hardware at the problem. It's about understanding the intricate interplay between hardware and algorithms. It's a real co-design challenge, right?
Absolutely. The guide emphasizes that even seemingly small improvements in efficiency can have a huge impact when you're dealing with the scale of LLMs. A 20% gain in benchmarks is meaningless if it comes at a 20% loss in roofline efficiency. It's all about strong scaling, achieving a linear increase in throughput with a linear increase in hardware.
That's a crucial point. And it's not just about compute either. The guide highlights the importance of understanding memory bandwidth and latency, especially interchip communication. We can easily become communication bound, right? The communication overhead can easily outweigh the gains from adding more chips.
Precisely. The guide breaks down the different parallelism schemes: data, tensor, pipeline, and expert parallelism, and how to choose the best one for a given hardware setup. It also delves into techniques like rematerialization and zero to reduce memory requirements. It's a very practical guide.
I see. And it's not just about the parallelism schemes. The guide also emphasizes the importance of understanding the transformer architecture itself, the sizes of matrices, where normalization happens, and the FLOP counts for both training and inference. It's about getting down to the nitty-gritty details.
You're spot on. They even provide a detailed walkthrough of the transformer math, showing how to calculate parameters and FLOPs. This is crucial for estimating memory usage and predicting compute and communication times. It's like, getting under the hood of the transformer engine.
It's fascinating how they connect this detailed understanding of the architecture to practical applications. They use LLMA-3 as a case study, showing how to estimate training and inference costs and times on TPUs. This is where the rubber meets the road, isn't it?
Absolutely. And they don't stop there. The guide also covers profiling and debugging techniques using JX and TensorBoard. It's a comprehensive resource, covering everything from theoretical foundations to practical implementation details. It's a must-read for anyone serious about scaling LLMs.
I agree. The emphasis on roofline analysis is particularly insightful. Understanding the limitations imposed by compute, communication, and memory is fundamental to efficient scaling. It's about finding the sweet spot where you're not bottlenecked by any one of these factors.
Exactly. And the guide's structure is really well thought out. It starts with the fundamentals, gradually building up to more advanced concepts and practical applications. It's a great resource for both researchers and engineers. It's a very well-structured and practical guide. I highly recommend checking it out.
I couldn't agree more. It's a valuable contribution to the field, bridging the gap between theoretical understanding and practical implementation. It's a game changer, really.
Thanks for joining us on Tech Bytes and News. We hope you found this discussion insightful. Until next time, goodbye.
Bye-bye.